Alright, all. I'm sorry this is late in the weekend, but I hope you do get a chance to watch. This is going to start out Chapter 15, which is going to look at something called the common ion effect and buffering. So we're actually going to go through sections 15.1 and 15.2 in your textbook, and I think we're calling this section 11.9 as far as our notes go. We'll start out with kind of addressing what a common ion is. If you take a look at the equation here, we have hydrogen cyanide, or cyanic acid, that's reacting with water to form the hydronium ion and this cyanide ion. And the common ion effect is essentially asking what happens when we add a common ion. So if we were to add a salt to this particular acid solution, and that salt would be sodium cyanide, NaCN, the equilibrium is going to shift to the left. The reason is because we are going to add more of this stuff. So if we add more of the cyanide, that increases the concentration on the left, which in turn, or on the right, which in turn shifts the concentration to the left. Remember, the sodium has no effect at all on the pH. It has no effect on the equilibrium because there are no other sodium ions in this particular equation. Because of this leftward shift, a solution of HCN and sodium cyanide is actually less acidic than just the sodium cyanide alone. The NaCN has the effect of actually recombining essentially with the H3O+, forcing to the left, so that takes the hydronium ion out of solution and thus actually raises our pH, or makes it less acidic. So buffers are actually fairly interesting, or these common ion effects are actually fairly interesting. So now to 15.2, it takes this idea of the common ion and addresses the buffered solution. A buffered solution just resists a change in pH. So the solution itself is maybe made by the chemist or made in the body to maintain a particular pH, even though some outside sources might come in and try to change that pH. That might not be good for the chemical that the chemist is trying to make, and that certainly is not good for the human body. Buffered solutions are weak acids or bases containing a salt with a common ion. We saw a weak acid, HCN, on the previous slide, the common ion, the cyanide ion, then coming in to raise the pH. After addition of a strong acid or base, we got to deal with stoichiometry first and then the equilibrium, and we'll actually address that a little bit later in this presentation. So what happens when instead of a weak acid or base being added into the solution, we add a strong acid or base? Does that really highly influence the solution itself? So let's first try to locate and identify some buffer systems. I've got three on here: KF and HF, KCl and HCl, and Na2CO3 and NaHCO3. Pause the video, see which ones you think are buffered systems. Alright, well, A is a buffered system. KF is a weak acid, and F negative is its conjugate base. That should say HF, ladies and gentlemen. Hopefully you caught that. Sorry about that. So that should say HF is a weak acid. HF is a weak acid, and F negative is its conjugate base. The K has no influence at all. So because of the weak acid and conjugate base pair, we have what we call a buffered solution. The conjugate base pair is going to force the equilibrium back to the left, and thus reducing the acidity or raising the pH. Now, in the second set, HCl is a strong acid. So in this case, we don't have a buffered solution. The KCl, yeah, it's going to add to the solution, but because HCl is such a strong acid, there is no such thing as forcing the equilibrium back to the left. It's just not going to happen. So if we look at an equation, we've got HCl plus water, and I don't even write the equals or the yield sign. The equilibrium sign. I just kind of write the yield zero to the right because of the incredible increase of the dissociation of the HCl. If we add more chloride by putting in potassium chloride, equilibrium states that, well, the reaction will shift back towards the left, but that's certainly not going to happen because the dissociation is just so strong with the HCl that the extra Cl will not go and hunt out the hydrogen and try to recombine with it. It'll force it back to the right every single time. Now, the last one's probably the most difficult. The carbonate and the bicarbonate. But if we take out the sodium in both of those things, we should notice that the carbonate is actually a weak base. Bicarbonate is its conjugate acid. It's the thing that accepts the proton. So this is a buffer solution, and in fact, this is the main buffering solution that occurs in our bodies. Our bodies are very sensitive when it comes to pH, and our pH of the blood has to really stay in an incredibly narrow range in order for us to survive. I want to say it's between like 7.2 and 7.4, and if we fall outside that range, then we actually have some serious issues and some serious problems. So I can talk a little bit more about that in class on Monday. Let's get into a sample problem then with buffered solutions. We're going to ask the pH of a solution containing 0.3 molar acetic acid, well, not acetic acid, I don't even know what that is, HCOOH, and 0.52 molar HCOOK, so the potassium ion is our spectator ion there. So we have a mixture of a weak acid and its conjugate base. All right, let's go find those things. Here's the weak acid, here's the conjugate base. And we can cross out the potassium because it really has nothing to do with our particular reaction. So let's write down our dissociation reaction then and think about what this stuff is going to do to our dissociation. It should add ions there, thus forcing our reaction back towards the left, thus actually lowering the pH of a solution that, or I'm sorry, raising the pH of a solution that contained only this stuff. Okay, so let's do our little ice table here. Now the difference is going to be that on the right side of the equation, you're going to notice right there, the 0.52, we actually have a concentration of our products, and we haven't had that in the past. Everything else kind of looks the same. Let's find some equilibrium concentrations. There's a little bit of a difference there too. Our Ka for this stuff is 1.8 times 10 to the negative fourth. And then we can go ahead and write the law of mass action for this particular process. We can solve for x, there it is, and then we can find the pH, and the pH is 3.98. Now, if you did the same particular idea, do the same exact problem, but take this stuff out of the equation, and just use that stuff right there, and I think you'll notice that your pH is going to be lower, and that's because it's not a buffered solution. Now, we have an equation that's really, really handy for these types of problems in chemistry, and it's called the Henderson-Hasselbalch equation. I'm not 100% sure that it's going to be something tested on, but it's a really neat shortcut for us to use. The Henderson-Hasselbalch equation looks like this. I hate throwing out equations and not telling you where they've come from, but the derivation of this equation takes a bit too long for me to go through on this video, and I'm probably not going to do it in class either. I know you're all curious as to where this stuff comes from, so if you want to take a look, page 688, 689 of your textbook will go ahead and derive the Henderson-Hasselbalch equation, and it is not a difficult derivation. There's no calculus involved. There's some logarithms, obviously, but it's really not that difficult. So go ahead and take a look at that, 688, 689, to see where this equation comes from. In general, the Henderson-Hasselbalch equation says the following. For a particular buffering system, that's a conjugate acid-base pair, all solutions that have the same ratio A negative to HA will have the same pH. So if we take a look at our first system that we had, if we have HCN and CN negative, okay, that was the first slide that I had. So if I had the concentrations of these things, it doesn't matter if the concentration of the CN, and I'm just going to pick some arbitrary ones here, change my color here. Let's say the HCN is 5 molar and the CN negative is 3 molar. That's going to have a particular pH. I don't know, whatever it is. Let's call it number. Okay? If I go ahead and I change those concentrations and I do it proportionally to 0.3 molar and 0.5 molar, the pH of that solution is also going to be number. It's going to be exactly the same. So the Henderson-Hasselbalch equation, as you're going to find out, is going to be quite a handy tool that's going to shorten up the actual math that we have to do. So we're going to actually go back to that previous problem that we worked out. And we're instead going to use the Henderson-Hasselbalch equation to figure out an answer. So we've got, again, a mixture of a weak acid and its conjugate base. Let's go through all the steps. There's your equilibrium. All right. So the common ion effect, again, is what we have with this HCOO, and it's forcing our equilibrium back to the left. We're assuming that X is essentially 0. So we can say that the concentrations, the equilibrium concentrations of our important ions are 0.3 and 0.52. If we go ahead and we use the Henderson-Hasselbalch equation, we actually have to use a number called the pKa. You may have seen that when I had first written down the equation. Well, the pKa, just think about it in terms of pH. How do we find pH? Well, pH equals the negative log of the H plus ions. That's how we get pH. Well, pKa is quite similar. pKa is going to be the negative log of the Ka. Okay, you know that Kas are traditionally really small numbers, and so they're kind of tedious to write. And when it comes to the Henderson-Hasselbalch equation, we're working in pHs, so we're working with things that are, you know, between 1 and 14. So we need our pKa to kind of follow that trend as well. So that's why we need our Ka to follow that trend, so that's why we actually use a pKa. The pKa of HCOOH, if you refer back to that previous slide, the pKa is actually 3.77. So if I plug all of my numbers into the Henderson-Hasselbalch equation, I get my pH equals 3.77 plus log 0.52 divided by 0.30. And my number is actually a little bit different. Okay, it's 4.01, and that's different than my previous slide had said. Let's go back up to the previous slide to show you that. Your difference is about 300ths. You've got 3.98 and 4.01. So the Henderson-Hasselbalch equation makes some estimations and some approximations. Since the initial concentrations of HA and A negative are relatively large in a buffered solution, usually this generalization is acceptable, so we can usually use that particular equation. And you'll see in the textbook they're oftentimes going to say, use the Henderson-Hasselbalch equation. It helps you out. It makes things go faster. Okay? If they know the approximation is not going to work out, they do not ask you to use it in the textbook. All right, let's advance then. And go through some of the slides we've already went through. Okay, and we'll come to this guy. All right, so our last problem, a little bit more involved now because it's going to incorporate a second part, which is going to add in a strong base. Let's take a look at part A first, calculating the pH of a 0.3 molar ammonium, 0.36 molar ammonium chloride buffer system. This is nothing different than what we did a couple of slides ago with the HCOOH. It's just now that we're dealing with bases, so we got a Kb instead of a Ka. Let's set everything up similarly to what we had done in the past. Here's our ice table. Again, the difference being that NH4 plus actually has an initial concentration. We have our changes, we have our equilibrium concentrations, we set everything up, and you could go ahead and calculate this out. We're going to approximate that X is negligible because it is really, really tiny as compared to initial concentrations. And our pOH comes out again to 4.82. If we want a pH, we can then subtract that from 14 and find 9.18. All right, super. Now, let's take a look at part B. What's the pH after the addition of 20 mils of 0.050 molar sodium hydroxide to 80 mils of the buffered solution? Sodium hydroxide we know is a very strong base, so if there's any lone protons hanging out, it's going to suck them up, it's going to eat them up. But if you'll notice, this is a pretty low molarity sodium hydroxide. Even though it's a strong base, the concentration is pretty low. So if we add a strong acid or base to a buffer, we have to follow these two rules. Whenever we're adding something, we're adding solution, we now have different molarities, and that's kind of a bummer. So we actually have to go back to the drawing board and recalculate the molarities of all of the solutions that are now involved. That includes the base, the conjugate acid, and this new strong acid. Number two, we then have to set up an equilibrium problem for the conjugate acid base, since the reaction is actually going in reverse. So then we got to remember, we got to do the stoic first, and by stoic I mean recalculating molarities, and then the equilibrium, the new type of equilibrium problem. So real quickly here, I've just calculated those new molarities. Here's the final volume. It's just going to be 100 mils, right? Because we're adding in 80 mils of the, or 20 mils of the sodium hydroxide. So I'd gone ahead and calculate the ammonium and the hydroxide ion. Remember, the sodium doesn't matter. And the ammonia with these new volumes. And you get these new concentrations, 0.29, 0.01, and 0.24 molar. Now, our equation looks different with the addition of the hydroxide. Okay, you can see that ammonium, NH4 plus, is now on the left side. Why is that? Well, it is going to actually eat up the hydroxide ions. So we're going to have an equation that looks like the following. Okay, that reversed equation. Let's take a look at two things now. Let's take a look initially at our starting molarity. Okay, again, 0.29, we got 0.01 and 0.24. Water doesn't matter. And then what about our ending molarity? This is the biggest point, I think the hardest point to grasp of these problems. The hydroxide is going to get eaten up totally. For every 1 mole of ammonium, NH4 plus, it will eat up 1 mole of hydroxide, OH negative. Well, I've got way more ammonium than I do of hydroxide. So the hydroxide is going to take away 0.01 ammoniums. That leaves no hydroxide left. But it should add a 0.01 to the ammonia. So what are we doing? We're forcing the reaction, we're forcing the direction this way, to the right. We are actually taking hydroxide, taking ammonium out of solution. Ammonium, again, being that conjugate acid, we're taking it out of solution. Okay. The Ka of H plus NH3 divided by NH4 plus is 5.6 times 10 to the negative 10th. We can then substitute in the important numbers there. Again, you might be asking, why are we doing a Ka, Mr. Koenig? Well, we're doing a Ka because this is the conjugate acid. Okay, so that's why we're doing the Ka. Notice NH4 plus on the bottom. So it's 5.6 times 10 to the negative 10th. How do we get that? Again, Kw equals Ka times Kb. We know the Kb of that dude. We know Kw. We can find Ka of that dude. Okay, we did that in class. So H plus comes out to be really, really tiny, and we get a pH equal to 9.20. Ta-da! There it is. Okay. Now, check this out. We can do this whole thing by using Henderson-Hasselbalch. Okay. The pH, again, equals pK plus log NH3 NH4 plus. pK is 9.25. Take the negative log of the Ka. You get 9.25. So you get 9.25 plus a log of 0.30 divided by 0.36. Now, hold on. That's 9.17. You might say, well, Koenig, that's not what we had before. Yeah, but we've got to remember something. These concentrations were the initial concentrations before adding the new stuff. Okay, so let's go ahead and do Henderson-Hasselbalch with the ending molarities, 0.28, 0.25. So now again, 9.25, that's the pKa. And check it out, 9.20. So cool, that 9.20 actually equals the previous slide. So holy man, Henderson-Hasselbalch, really nice, really shortens up your work. The biggest thing that you have to figure out, what are these numbers right here, 0.25 and 0.28, that comes from this stuff. These come from recalculating your molarities, and then we can use Henderson-Hasselbalch and make life a lot easier. Alright, so last slide here. Sorry, we're going on 20 minutes. Buffered solution characteristics. First of all, buffers contain relatively large amounts of weak acid and corresponding conjugate base. When we add H+, added H+ reacts to completion with the conjugate base, so the H+ goes away. It is essentially what you would say your limiting reactant. And the opposite is true with hydroxide. Added hydroxide reacts to completion with the weak base. It, again, should be your limiting reactant. So those are some of the characteristics of buffered solutions. Okay, buffered solutions. And we'll do a whole bunch of problems of these in class on Monday, and hopefully hammer down some buffered solutions. Alright, so that's 15.1, 15.2. We only have 2 more sections until we can hit up our lab and get out of the textbook for a couple of days.